face when I'm with you, but I love it, but I love it.
And welcome to the video on functions of two or more variables. So this video is kind of like, the title said it all. We're going to be looking at functions of two or more variables, and usually we'll be dealing with functions of two or three variables, one or the other. Going into four is a little bit tricky. So anyways, an example of a function of two variables, let's start with, is the area of a rectangle. So if we have the area of a rectangle, we know, or we should know by now, that that is equal to base times height, right? So basic geometry, base times height. And these two things, we could represent base with the variable x or something like that, and height with the variable like y, okay? So these are two independent variables, right? So our area is dependent on two variables. Therefore, this is a function of two or more variables. So in this case, this is like a multivariable function, right? So we have one variable here and another one there. So this is a two-variable function. Now let's look at another one. How about distance? Okay, so we'll have the distance formula here. So distance in space now, in space of a point to the origin, point to the origin. Okay, so in this case, space meaning 3D, right? So three-dimensional. So our distance formula is going to look like x squared plus y squared plus z squared, and this is to the origin. So like everything is minus 0, right? So there's our square root sign. So here we have three different independent variables, right? So x, y, and z. So this is a three-variable, multivariable function, okay? So of three variables. More generally, we'll say that, so this is a general formula. So generally, our multivariable function, or our function of two or more variables, looks like we have an f of x sub 1, x sub 2, comma, dot, 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 until we get to x sub n. So this is a function. This is a function of n variables, okay? Function of n variables. So if n were 4, then we would have a 4-variable function, right? Okay, so again, going back to what I said was probably one of the most common ones that you'll see as far as the number of variables is f of x sub 1, x sub 2, and x sub 3, okay? So this is a function of three variables, and usually we actually see it as f of x, comma, y, comma, z, because it's easier to differentiate as opposed to having all these x's and then looking at the subscripts, etc., etc. So anyway, so this is a function of three variables. This is a very common one that we will be working with throughout the rest of this course. And sometimes what we'll see, so x, y, z, we can think of this as like the three axes that we've learned, right? So here's our x, there's our y, and here's our z, sticking up or down, right? There's our z-axis, x-axis, and our y-axis. Okay, so these three variables form the structure for space, right? 3D space. Anyways, so sometimes, here's a special thing, and we'll also see this as well. So sometimes we see a function such as g of x, comma, y, comma, and instead of z, we see another little function of x and y. So this third component here, this z, we can call it z still, right? It's in the z position. So that means like going up, how much you go up or down. This is dependent on the first two variables, which are independent of each other, right? X and y are independent completely. You can move anywhere you want on the xy plane. But then the height is determined, so I'll write that down. Height is determined, determined or dependent on, I'll say, dependent on position in the xy plane. Position in the xy plane. xy plane. Okay, so this is what we're going to call our surface, right? So our surface, like the height up here, that's determined by our point on the xy plane. Okay, so that determines our z coordinate, or our z coordinate. Okay, so let's do a little example of this. Well, an example of something that we'll have to watch out for when graphing surfaces and considering surfaces. So what we're going to do first is sketch the domain. So sketch domain of f of x comma y is equal to the square root of 4 minus x squared minus y. Okay, and we're going to identify its range. Identify its range. So before we even, so this function that we see here, that is a function of two variables, right? Our x and y are independent. Okay, and this will be important when we do plug it into that z spot, right? When we're working with three variables. But anyways, right now we'll just look at this as a function of two variables. Okay, so what is the domain? So domain meaning what can you possibly plug in there for our x and y? Like what is the whole I'll just say the range of possibilities for our x and y coordinates there. So because it's under the square root, this 4 minus x squared minus y, this whole quantity here must be non-negative. We want it to be non-negative, right? Because you can't take the square root of a negative number. It's just not possible unless we go into imaginary, which gets super complicated. And we're not going there right now. So anyway, so we want this whole thing to be greater than or equal to 0, right? It can equal 0, that's fine. The square root of 0 is just 0. But anyway, so let's say we do this. Now what? So what we want to do is figure out, like I said, what can y and x be? So for example, on this one, I'll just get y by itself, okay? So I'll move it over to the right side, and then just look, so we can get it into a form that is more understandable for us to graph, okay? So this is what we have, this inequality. So y is less than or equal to this thing on the left side, right? So this basically means all of everything, so all points, all x, y points, that is, I'll stick that in, all x, y points below the graph of, y equals negative x squared plus 4. I just rearranged that, right? 4 minus x squared. Okay, so this graph, I'll do that on the next slide, okay? So what we have is, we want all the points below our negative x squared plus 4, okay? So if we graph that, we just have something, a downward facing parabola, right? So 1, 2, 3, 4. And we have a 1 and a 2, 1, 2. Okay, so this has the y-intercept of positive 4, right? 0, 4. And then it points down, but it's a normal parabola, so it goes something like this. Okay, so we have something looking like a downward facing U. Okay, and it goes up, and then it comes back down. Okay, so we have something like that, and it says all points below. So it's going to be this whole entire area under here. It could be x and y can only be within the shaded area. If you pick a point out here, that is going to make our square root, everything inside the square root, negative, which is impossible. So we don't want that. We want everything below the u. Okay? So that would be our domain. Okay? So domain is this thing. You could list it as that. And now what is our range? What does that mean? So range is equal to what? So let's go back and we'll write down our two variable function. So f of xy is equal to the square root of 4 minus x squared minus y. Okay, so range meaning like what values can our function possibly take on our entire domain, right? What is the range of those possibilities? So we said that this inside quantity must be non-negative. So that meant that 4 minus x squared minus y is greater than or equal to 0. Okay? So if we were to say square root both sides, square root the left side and square root the right side, what we would get on the left is our function exactly, right? So 4 minus x squared minus y, that's what we want. And then we have a greater than or equal to 0. So 0 just stayed 0, right? So what this means is that our function, this thing on the left, which is equal to f of x and y, must be greater than or equal to 0 at all times, right? So what this means is that our range, the lowest value that our function can take is 0 itself, so that's our left endpoint here for our range. And then it could go greater than, right? So it doesn't really have a bound on the upper side, so that means that it can go all the way to infinity. Okay, so this is our range. So this is range, and this one was domain. Okay, so now that we got that necessary step out of the way. I just wanted to address the domain and range thing. Now we'll go back to what sometimes we see for a a function of three variables. So x, comma y, comma f of x and y. Okay. So here, as I said before, our f of x, comma y is going to be our z. That's in the z spot. So this basically represents our height, how much we go in the positive z direction or the negative z direction, right? So this depends on both the x and y coordinates. So it depends on x and y. Okay. All right. So what are we gonna do with this? That might look a little bit tricky, mainly because we haven't seen that before, right? So what we're gonna do. A certain way to analyze a graph, especially like a surface, right? Like what this represents, is through something called traces. Okay, so traces. These are going to be pretty big in analyzing graphs and surfaces. So what we're going to go over first, there are the vertical kind. So there are vertical and there are horizontal ones. So vertical and horizontal. We'll go over the vertical ones first. Okay. So let's do. Let's see. I'll start the vertical traces on the next slide. So a vertical trace, so vertical traces. So for example, let's say we have, so again, this is a way to analyze, any kind of trace is a way to analyze a graph. Analyze a graph such as our f of x, comma y. Okay, so what is a vertical trace? Basically, we'll start with a graph here with a surface. So here's our x, our y, and our z. So let's say our surface looks something like this or something like that. Okay, something a little bit crazy. Looks like kind of like a flying carpet, sort of. Anyways, so let's say, because every point down here, every point on the xy plane, so this is the graph of x, comma y, comma f of x, y, okay? This surface that we see up here, the carpet thing, that is our f of x, comma y, okay? And all the points down here, anything in the domain, right, anything we plug in for x and y, that is going to be like in the xy plane, all right? But then each of those points is going to translate, once you plug them in, onto a point on our surface, okay? So our point, dependent on that xy down here, that's going to exist on the carpet, okay? So our final graph is just going to be this entire like magic carpet thing, the flying carpet, okay? So anyways, so what is a vertical trace? Now that we know what kind of like a general idea of what this graph looks like, a vertical trace is basically what we can do is, first of all, we'll deal with our x coordinate, okay? So let's say we set our x, we freeze it at a constant. I'll just name it constant a, okay? So here what we're going to do is take this, we'll take x and set it equal to a. Here's a, okay? So I'm just going to draw like a little dashed line here. So we want x to be constant. So what that does is it creates a plane, which is parallel to the YZ surface. Or YZ plane, okay? So this plane, at x equals a, this is a plane, a vertical one, actually. So a vertical plane that does what? It's actually going to cut through our surface here. So it's going to cut through and make a little, like a curve on our surface, right? That cuts through f of xy. Cuts through the graph, okay? And what this means, like, formulaically, I guess you could say. So here was our original graph, right? But now, if we set all of our x's equal to this constant a, what we're going to get is a, comma, y, comma, f of a, comma, y. Okay, so this is the formula for our vertical trace. So vertical trace, I'll just abbreviate here. Vertical trace by setting x equal to our constant a, okay? So, anyways, so this is what it looks like. This is the curve in the x equals a direction, right? And now let's see what happens when we freeze our y at a constant. So if we have that same graph, I'll just draw it really quickly here. So x y, and z, and we have our carpet flying around up there. Okay, so if we have that, this is our x, y, f of x, y graph. Okay, and let's say now we set y equal to some constant, I'll call it a b, okay, so we don't mix it up with the a that x was. So this is an entirely different vertical trace, okay? So this is a vertical plane, again, vertical plane that does what? Let's see on our graph. So let's say we set y equal to b, okay? So let's say b is here, right? So there is equal, y equals b, so now we're going to draw a line through that. And this actually, if we bring it straight up, it's going to make a plane. And this one's kind of going away from us a little bit, okay? So it's kind of going like that. And this one's going to cut a curve through, okay? So what we're going to have is something looking like, maybe something like that, a little bit. It's kind of straighter than the one that we saw before, maybe because it's going away from us. Anyway, so this is also a vertical plane. This is an entirely different vertical trace, okay? Because you can't set, I mean, if you set x and y equal to constants at the same time, you're just going to get a point on the bottom, right? Point down there, and it'll translate to a point on the surface. So anyways, what we're doing is setting them equal to constant separately. Okay, so we did the x, and now we're doing the y separately. So this is a vertical plane that cuts through the graph again. Cuts through, and I'll just say graph. Cuts through our graph, okay? And let's see what this one says as a formula. So we have, this is what we had in the beginning before we set anything, before we froze any constant, any variable to a constant, but now we're setting y equal to b, so our new equation for this vertical trace is going to be x comma b comma f of x comma b, okay? So this is the equation, or the formula, I guess, for this curve right here, the one bolded, right? That's our vertical trace at y equals b, okay? So let's do some practice. We can work on an example of a vertical trace. So,
And I know she'll be the death of me. At least we'll both be numb. And she'll always